Welcome back. We were discussing the fundamental of electronics, different diode circuits. This is the last lecture in the series lecture 3 where we discuss different diode circuits. So the topic that we will take here is peak-to-peak detector and its various variations. We have seen that in half-wave rectifier using the capacitor input filter, we produce a DC output voltage which is approximately equal to the peak value of the input signal. So whatever the transformer secondary will give you the peak signal, the half-wave rectifier will produce the same value of that peak signal, and the capacitor input filter is used. What is a peak detector? It is basically a circuit which is having a small signal diode, and that converts the rectified circuit into a peak detector circuit. It operates at a higher frequency than 60 Hz. So the frequency of operation should be more than the power frequency. It is used in measurements purpose, the signal processing purpose, and the communication purpose. There is one variation which is known as peak-to-peak detector. It is basically cascading a clamper circuit that we have studied with a peak detector. So we will see how the peak detector circuit is connected in cascade with the clamper to form the peak-to-peak detector. The output of the clamper is the input to the peak detector. So whatever the output will come from the clamper, it will go to the peak detector circuit. The peak detector provides a DC voltage equals to twice the maximum value of the secondary output voltage. So this is the circuit. The input we have AC signal whose maximum value is BP. This is coming from the secondary of the transformer. And then we have seen in the previous lecture the use of clamper circuit where a capacitor and a diode will push the output signal to a value 2 BP, and this will be above the zero time. So in the approximation case, this will be 0.7 volt, but ideal condition you will have 0 volt. Then you have a diode and another capacitor connected, and at the output load register, you are getting an output which is twice the voltage peak of the secondary of the transformer. If you talk about the time constant of this circuit, which is the RC time constant, it has to be much greater than the period of the signal. So whatever the signal time period is there for the input, it has to be much greater. Then only effective clamping and peak detection is possible. It will also ensure the small output ripple in the signal. The application, if we talk about these type of circuits, it is used for measuring the non-sinusoidal signals. So measuring sinusoidal signal is easy with the help of voltmeters and ammeters. But if you are measuring the non-sinusoidal signals, which may be in the form of triangular or in the form of sawtooth, then the ordinary AC voltmeters, which is basically reading the RMS value of the signal, this will be incorrect when we go for the non-sinusoidal signal. A peak-to-peak detector output to a DC voltmeter, if we are using for the measurement, it will show the peak-to-peak voltage. For example, if a signal is swinging between minus 20 volt to 50 volt, then the voltmeter will be detecting 70 volt, because this is the range which is 70 volt you have between minus 20 volt to 50 volt. So the peak-to-peak detector will be detecting 70 volt, and this is non-sinusoidal in nature. We talk about voltage multipliers next, and different variations of voltage multiplier, starting with a doubler circuit. So we have voltage doubler. So voltage multipliers basically use rectifier diodes and operate at power frequency which is 50 to 60 Hz. This produces higher DC output voltage using configurations like the voltage doubler. So when you require higher DC output voltage and the power frequency, which is 50 to 60 Hz, then we go with voltage multiplier, and we will first see the voltage doubler and then the other variations. So it is similar configuration as peak-to-peak detector, whatever we have discussed. And here the clamper will add a DC component to the secondary voltage. So we have a step-down transformer. The input we have coming from the power supply, which is we can take 120 volt 60 Hz. Here the voltage will be much lesser because it is a secondary, will be step down. Then we have the clamper circuit here. So clamper circuit is there and we need to double the voltage. So clamper circuit will be there, and then the peak detector signal with circuits will be there. And at the output of the load register, we will be getting twice the peak voltage. So here, if the voltage is Vp, then at the output we are getting 2 Vp. Remember, when we discussed the half-wave rectifier with capacitor filter, we were only getting Vp at the output. So why we want to use a voltage doubler? The question is, so if we are using a transformer and we adjust the turns ratio, that will work for lower voltage. For very high DC output voltage, if you want, then the step-up transformer alone can be bulky and impractical. So we need not to use the step-down transformer, we have to use step-up transformer because we need high voltage. So that will become bulky and impractical. And hence, we go with voltage doubler, which allow for smaller transformer and simpler design. So transformer will be small and design will also be simple, and hence we will get high DC voltage. If we take an example like where the line voltage is 120 volt RMS, then we get 170 volt peak. So 120 volt RMS is equivalent to 170 volt peak. And in order to achieve a high DC voltage, let us take an example 3400 volt, then it will require a step down transformer of 1:20. Using voltage doubler can reduce the transformer size and complexity. So we have a step up transformer which is 1:20. This is quite bulky in nature, hence we can go with voltage doubler. This will reduce the size as well as the complexity of the circuit. What about the other variations if we go with the triplet circuit? So voltage tripler, this will add an additional section to the doubler circuit. So voltage doubler we have seen, and one more section we need to add it. So that will become triplet circuit. At the peak of the negative half cycle, the DC forward biasing with there and charging of the C3 capacitor to give 2 Vp. Now here we have step down transformer with AC input, and we are getting the peak value here at the output of the transformer. We have the voltage doubler variation. So what we are adding is another one more additional section to the doubler circuit. Then the peak of the negative half cycle. Now remember, this is a half wave rectified circuit which is in the form of tripler. So the output that we are getting, the tripler output, we are getting across the C1 and C3. So that is the voltage we try to measure across C1 and C3. And these output voltage will be approximately 3 times the peak voltage that is appearing across the secondary of the transformer, and the time constant will be long. So it will have long time constant. Now, if we want to have 4 sections, that is known as quadrupler, and that is basically we have one more section which is adding to the first 3 section of a tripler. The 4th section will be adding, and whatever the voltage Vp we are having at the secondary of the transformer, that will give 4 Vp now at the quadrupler output of across the capacitors. This will again increase one more section to the triplet circuit, and we are getting more output voltage. So what are the key points that we need to remember is, theoretically we can say that sections can be added indefinitely, but what will happen, the ripple will increase with each stage. Voltage multiplier are basically suited for when we need high voltage, and high voltage means low current applications, such as an example of CRTs, cathode ray tubes. So it is not practical for low voltage. So we do not use it for low voltage applications. We use only for high voltage applications because there will be increased ripple. So as you increase the number of sections, the ripple will increase. So if we talk about the voltage multiplier variations, different type of variations, then we can have either floating variations or grounded load variations. So what is floating load? Where the original voltage multiplier have the load which is neither end is grounded. So you do not have any ground connection. Whereas in grounded load, the variations comes because different application you may have where the load is grounded. So if you talk about the example of the variations in the grounded mode, which is in the voltage doubler, it is similar to standard doubler but with added ground connection. So you need to have a load resistor which is grounded. Then it will have grounded voltage doubler. If you want to redesign any triplet circuit or quadruplet circuit, then the configuration adjusted to accommodate grounded load. So this is quite little bit complex as compared to the simpler circuit. The choice will be there between floating and grounded design depending upon what specific application we are dealing with. So CRTs may have floating load design. So if we see one circuit example compared to the previous one, what we discussed, the doubler, tripler, and the quadrupler, here the load register is basically grounded. So it is in the form of grounded load variations, where the before sections, whatever the arrangement we have is a little bit changes whatever we have seen from the previous variations. So previous variations, we were having the output between the two capacitors. So across the capacitor, we were measuring the voltage, which is floating. Now we are measuring voltage across the load register. So it is grounded. Voltage doubler in the form of full wave, if we see, where we need two diodes, D1 and D2, and they will be operating in the positive half cycle and negative half cycle. So the upper capacitor C1, which is connected, it will charge the peak voltage. So whatever the peak voltage we are getting here, PP, it will charge for one polarity, and other capacitor C2, which is in the downward, it will charge for other positive polarity. So you will be getting 2 Vp at the output voltage when the load is light. So what are the advantage when we go with full wave over the half wave design? So first, the ripple frequency will be higher. So output ripple frequency will now be 120 Hz, which was 60 Hz in half wave design. And the filter will be easier because due to higher frequency, it will smooth the DC output. So when we go with higher frequency design, the DC output we are getting much better. If we talk about the diode rating, the peak inverse voltage rating of the diode only needs to exceed Vp and allows use of diode with lower voltage rating, which will reduce the cost and complexity. So it is better in terms of peak inverse voltage, it is better in terms of ripple frequency. So we have covered the entire lecture 3, and let us do the summary whatever we have discussed in lecture number 3, because it is quite a big unit discussing about the diode circuit. So we have discussed the half wave rectifier, where a diode was used in series with a load resistor. You were getting one half signal of the two polarity, positive, negative input voltage. The DC output voltage is 31.8% of the peak voltage of the secondary of the transformer. So we require a transformer which is in the form of step down configuration, means voltage will be decreasing and current will increase. So secondary voltage we can compute using the formula voltage secondary is equal to voltage primary by turns ratio, and the turns ratio is in the form of step down. We have discussed the full wave configuration as center tapped or bridge rectifier configuration. Center tap will have 2 diodes, whereas bridge rectifier will have 4 diodes. The output of full wave rectifier in the center tap configuration will have a peak value which is half of the secondary voltage. And the average DC voltage, whatever you are getting, that is 63.6%, which is double of the half wave rectifier. So here we are getting 31.8%, here we are getting 63.6% of the peak voltage. Here the ripple frequency is also doubled, which is 120 Hz, and these remain the same or whether it is full wave rectifier or whether it is bridge rectifier. The output DC voltage is also 63.6% of the peak voltage, similar to center tap. But here the full wave signal with peak value will be equal to the secondary voltage, similar to the half wave rectifier. So here we have the half value in case of center tap rectifier. So here we have full value. We discussed different type of filters like choke input filter or capacitor input filter. In choke input filter, we have NC combination, inductor capacitor combination, and the inductive reactance was greater than capacitive reactance. It passes the average value of the rectified signal to the load register. Whereas in capacitor input filter, you passes the peak value of the rectified signal to the load register. Ripple typically less than 10% you are getting in capacitor input filter, and this is most widely used in power supplies. So capacitor input filter is widely used as compared to the choke input filter. We discussed 2 important terms, that is the peak inverse voltage and the surge current. Peak inverse voltage is nothing but the maximum voltage which the diode has to withstand when it is non-conducting. Surge current, it is a brief large current when power is first turned on. So when the power will be turned on, the diode has to withstand a very large current, that is known as surge current. We have discussed certain circuits like clippers, limiters, clampers. So clippers will save the signal by clipping either the positive part or the negative part. Limiters, other name is diode clamps. It protects the circuit from excessive input. So it is protective circuit. Now there is a difference between clamps and clamper. So clamper is basically shifting the signal by adding DC voltage. Diode clamps is protecting the circuit. So clampers, peak to peak detector we have discussed, produce a load voltage which is equal to peak to peak voltage. So we are getting peak to peak voltage with the help of clampers. We have discussed different multiplier circuit in the form of doubler, tripler, quadrupler. So doubler will have the output voltage twice the peak value. Tripler will be multiplied with 3 and quadrupler will multiply with 4. And these are used in high voltage power supplies because we don't want to use the step-up transformer which are costly and bulky. So these complete the entire lecture 3 of Fundamental of Electronics, and we will move to lecture number 4 in the coming lecture. Thank you for now.